And this parabolic, it really is showing up in a very math way, which is if I have some reductive group G, I can imagine inside here we have a Borel. Right? So you think if this is a matrix group, we like to think of this as upper triangular matrices. And then from the Borel, I can take a quotient to T, which is just the abelianization of this. So this is called the universal proton. This is Borel. And the story in general is for some reductive group. Like this. And it's a sort of a feature that shows up widely in math all over, is that I'm thinking about my reductive group and things are a bit dicey, a bit complicated. And so I want to move my theory to be thinking about this maximal torus, which is commutative. So this process of going between these two is called parabolic reduction, and that's the sort of parabolic we'll see. It's the same parabolic stuff that showed up in Julia's talk. Okay, so there's that. I want to do a recap of the main characters we saw yesterday, because we're going to be trying to recreate the story from yesterday, but with some feature that looks like this parabolic reduction. So the first thing that I sort of got us to talk about was the evaluation functor. Things in this category of ribbon graphs. So these were a bunch of graphs, and they were decorated, and it landed in C itself, R2C. And once I had my evaluation functor, I could get from that Skein relations on the Hom spaces of rib C. So if I just had two objects here, two of these graphs, I had some Skein relation. And then from Skein relations, I made some things I called Skein categories. So these were written Skein cat. They depend on the choice of the ribbon category, and they depend on some surface. And then, so what do these look like? Well, these look like my Hom spaces, which were really the main characters here, is I take my surface sigma, and I thickened it, and my morphisms look like embedded graphs in here. So something like this. Like that. And they were all oriented and colored by objects of my So those were the basic constructions, and the final basic construction that I also got here were Skein bimodules. And if you recall, these were functors. I'll write Skein underline M, and it went from the product of two Skein categories. And these were all so these are the constructions that we were looking at yesterday, and today we're going to see how we can generalize this. I'll say now, this is, unlike everyone who gave a Gong Show talk, I did not memorize the archive number, but this is recent work with David Jordan. And if you want to look at the paper where it's all described, in a paper way instead of in a talk way, it's called parabolic Skein modules. So, if you want a paper reference, that's it. Okay, now what we want to do, we want to add defects. And what do I mean by adding defects? Well, I mean, if I look at this three-dimensional space, right, it has some, let me see, over here. Afton was thinking about a thickened disk. And now the sort of situation that we ran into actually with, we're trying to work out this paper, is I want to have on one part of my space one set of relations. So here sort of I want my Skein relations to depend on some ribbon category C, and here maybe on some ribbon category A. And the question is, what do I put in the middle? So what sort of data do I need to put here in order to define a defect in this? And I want to make a connection. This is really agrees some with the physics definition of defect. It's really a submanifold carrying some extra data. So we're trying to figure out what that extra data is now in this talk. So let's start thinking about what sort of nice features we have of Skein categories. And one of the first important features was to consider this functoriality. And what was the functoriality? Well, before it was between some category surf, and its objects were disks, and the morphisms were embeddings. And then so there's one morphisms, two morphisms. There are isotopies. And from here, I had a functor to something called cat, K, and this is the category of the two category of K linear categories. Like this. And this turns out to be a really important feature. So what I want to do when I'm thinking about what data should go on this defect is I'll say, well, whatever I do, I want it to make sense of this functoriality. So what I'll do is I'll add here, I'll make this as a and I'll say, well, I have A disks. I have disks with a defect in it, so it's A and C. And then I have my disks with C. And here, my embeddings, I want ones which respect the labels. And here I also want isotopies which respect the labels. Yes. Okay. So now what I'm going to do is I'm going to say, okay, I'll have some functor like this, and just knowing that whatever this object in this category gets sent to, like the fact that it's the image of a functor and it has embeddings and isotopies will tell me a lot about what structures I should expect. So just to write that down, I'll make some functor f here, and then I'll say f of this defect disk is the data on the defect. Other questions? So what do we want? Well, we know we need, actually, write it here. So what do we get on F? So first off, this thing, I'll just call it D for now, for defect, is a K-linear category, right? Just because it's the image of a functor that lands in K-linear categories. What else do I have? Well, if I draw it, I'll draw it like this. So if I have two disks here, one thing I'll ask here is I'll ask for my surfaces to have a sense of disjoint union. So this is also an object in my category. And here I want this to be sent to Delaine-Kelly tensor product. You saw the Delaine tensor product during Lydia's lectures yesterday. So if I have two disks, I can embed this into one disk, just like this. I'll draw the little images here. Right? And because this is an embedding, and f is a functor, I want this to be sent to a, sorry, this is a 2 functor, I want it to be sent to a functor here. So what is this going to give me? This is going to give me the sensing d to d, like this. And I also have another thing I want to add here, is I want to add, so stuff like this, and I also want to add the empty. So I have always also an empty embedding into this disk. So this is going to be this is going to look like a unit. And altogether what I get is that D is a monoidal category. So I know that whatever I put on my defect, it has to at least be a monoidal category. What else do we have? So we'll continue the structures on D. Well, I also can embed an A disk next to this, let's write it like this defect disk, next to the C disk. I can embed that into my disk. So I can embed it like here, here, and here. So up here A, that C. Right? And what is this going to give me when I apply F? Well, if I put F everywhere, what I'm going to get is something that goes from A box tensor D box tensor C to D, like this. Right? And we can see, if you start playing around, that this here is going to be a bimodule. Oops. Bimodule structure. So not only do I have a bimodule structure, but it's also it's compatible with all I'll just call them monoidal making. Embeddings. So what I get in total is that D is an algebra object in the category of AC bimodules. So this is the sort of data that I'll consider putting on my defect. And then you asked me about Merida category stuff. So whoever asked that, we're secretly doing alg 2 of cat sort of stuff here. Okay, so we have that. And then here's a proposition. This is equivalent having some weighted functor. This, where this thing here means opposite. And this thing is the Drinfeld center. We saw yesterday, which is just to recall pairs of D, an object in here, and then I'll call it sigma sub D. A natural transformation that switches which side D is on. Like this. So this is the sort of data that once I have it, I can start thinking about what I put on this, what this defect will act like. Are there questions?
So I mean, you have two functors, parameterized by these two categories, C and D, from the original surface category to cat K. The other natural thing you might try to do is just build a natural transformation between those two.
Yeah.
Do you have a comparison to that?
I'd have to think about it longer than would be reasonable right now. No. That's a good question. Yeah, so maybe the reason why this is the way that we're thinking about it is there's a 4 categories, objects of braided tensor categories, and these things are the one morphisms there. So we're just working with a different setting. Okay, other questions? Okay, cool. Let me give this thing a name. This thing I will call H comma sigma. Like that, where H is just to D, and sigma is this extra half braiding business. Okay, so now I've made some argument about what sort of data, but there's nothing really skeiny going on. Yeah, I can switch keyboards. There's nothing really skeiny going on. So the next thing I want to consider is how do I fit diagrammatics into this? All right. And what's happening is I've made the argument that such a functor is going to be giving me the data, but I actually haven't described this functor for you. I haven't told you what the relations are. It's, we don't have like a skeiny story for extending it to a general 3-manifold or surface. So what I want to do now is explain how this works. So here's my definition, rib sub D. So I'm going to say D, and I'm going to mean all of this data, this H and sigma and D all together, but we'll just write D. This is the linear category. So my objects, I'm going to call them D-labelings. And what they're going to look like is I'm going to take this disk I want to understand, and then try to be good about drawing the defect in blue. And what I'll allow myself to do is on the A side, and I have the C side. On the A side, I can have objects in A, so B would be A prime. And on the C side, I can have objects in C, W prime. I can have a bunch of points like this. So just put that in words. These are going to be these oriented framed colored 0 submanifolds again that we had yesterday when we were talking about evaluation, but now it's just the color depends on the side. And I'll note you can set it up either way, but I'm not going to allow points on the defect. Just that turns out to be better for our geometric thing we're thinking about. So here are the objects. My morphisms are, this up a little bit, these are going to be stratified. Maybe A, B, C colored ribbon graphs in this stratified space. So what is this going to look like? Maybe I can draw it up here where I do it. No, because I don't have to cover this. So what will this look like? These will look like graphs. They can cross the defect, but wherever they cross the defect, I need to have a coupon. And when I say this coloring business, it's just the color has to be in the right category for the region it's in. And there's a sort of one little question that can show up here is, if I have a defect really on the, a coupon really on the defect, there's sort of three categories floating around, right? But my coupons in Skein theory, I always just want to put a morphism in some category. So what goes on there? So here we can zoom out or zoom in. So I have a coupon on a defect. So let's say it's going like here. Let me just make sure I don't change the orientation from what I described. Okay. Let's say they're both oriented in, and this will be some dA, this is some dC. And here I need some morphism F. And what the morphism is going to be is it's from the tensor product of the incoming edges to the tensor product of the outgoing edges. In this example, there are no outgoing edges, so this will just be to the monoidal unit of D. And here I use H just to make sure my objects are all in D. So that's the sort of thing that comes here. What else should I mention? So stratified, this thing, they're going to be up to stratified isotopy also. And what's the picture that we should have in mind for stratified isotopy? Well, if I have my defect here, and I've embedded my skein like this, just a top-down view, this stratified embedding is not going to be isotopic to, let's say, this one here. Right, so these are, I'll write it in red, not stratified isotopic. But I could say just change where I cross, so I could switch it all over here or something. So these two are, yes, stratified isotopic. Okay, so this is my setup of my graphs that I want to use to understand morphisms sort of involving this defect. And now we can write down the theorem. So we have this. What are we missing? We're missing this evaluation functor. But here's what gives it to us. Position. Following procedure. So what I want to do with this, so I'm going to make a procedure, it's going to define a functor. What I want to do is I want to take this category and then try to get a functor into D. And what I'll do is first I'll project all of my ribbon graphs onto the defect. So what does that look like? That looks like I have this. And maybe I have something that's going on this side, and maybe I'll have something going on this side, just to make the drawing easier. And what this operation will do is I will just now have on the plane two curves like this, like that. Okay. But now I have a sort of a problem is here if this was colored by some B and A and this is some B and C. I want to get everything into the defect world, into this D world, so now I'll have this will be H of V, H insert unit, and the other one will be H of unit insert VC, like this. So those are in. But what I'm leading up to is planar diagrammatics, and there's no crossings allowed. So what I need to do with the crossings, so here, the crossing, I will use the half grading to, I guess, replace or maybe understand the crossings. So what does this look like? I had something like this, and I'll just replace it by, and this will be sigma with the right indices. So that's the first step, right? Is I'm going to project things here, and the second step happened early on in yesterday's lecture. Is I'll use planar diagrammatics to evaluate in D like this. But here we run into a little problem. To get planar diagrammatics, I need something pivotal, and so far with the functor description, I wasn't forced to this thing be pivotal. So here I have an extra thing, which is I need for the pivotal H respecting the pivotal structure. Yes. Okay, so if this was the first step here, then the second step, my color coding, which is now looking, I've made a bunch of boxes like this. My second step is to just turn this to some morphism, and here it would be like this. The example, or maybe I didn't. Yeah, they're in the same order. So like this. Other questions?
I have a stupid question.
Yeah.
So if you're crossing two strands,
Yeah.
then don't you get two different choices of sigma one from each strand, and then how do you know which one you
That's
choose?
part of the proof is showing that it's
Oh,
compatible.
okay.
Yeah. So the question was, I pushed H from one from one side, the other from the other side, so there's two half gradings, and it can't depend on which one I choose. Yeah. This is also, I'll just say, because you asked, the fact that one's coming from one side and the other's from the other side is also the same miraculous reason that we have a braided opposite up there. This one's in the mirror world. Okay, let's do the idea of the proof. So you need to show this compatibility, but one of the big things that you need to do is if I'm looking down at my defect, and I cross like this, right? So here I'm looking like down on my cylinder. This is isotopic to, I just draw it again, if I crossed on the other side. So like this. So these two are stratified isotopic. So a big thing of the proof is you have to show that these agree. On this functor, I'll call it RT. So this thing will be what RT represents. And then once you have that, the main part of the proof is something like doing some more complicated, some mixed versions of the Lagrange series. Right. Which comes down to showing that this step where I projected, which isotopy class I decided to project and which projection I used, it could be a nightmare to prove that you're independent, except for someone already did that, when they were talking about knots in the first place. So this is the two, I would say, key points of the proof. Okay. So now I've made a functor. And now I'll say is now we have defect Skein relations. Right? So it's just two sums of these tangles. I'm not feeling the inside drawing. The right colors. So this is maybe from I equals 0 to n, j equals 0 to m. And then here I have my defect everywhere. I'm really sorry for everyone taking notes in just one color. Or maybe the colors aren't that useful. So I have that, and then I can have whatever defects. This, the same things. That. Where these will all vary. So I have my defect relations. With those, now I can build defect Skein categories and modules. Right? Because before, as soon as I had this Skein relation, I could say, what would I do on surfaces? So my tablet rebooted. I guess it crashed. Okay. So I'll just define that. So now we have these defect Skein categories. And just to make it clear what's going on, these are, so given this A sensor C, weighted opposite, and now I want sigma. Sigma is now allowed to have A and C regions, so sigma A union over some curve, say gamma B, over C. The stuff, Skein category for sigma as objects so if I have something like this is my surface as objects, just what we talked about before. Like this, these label points, and then my morphisms and this whole thing. Like that. So now my Skein category will still be spanned by these things, and it's going to be up to Skein relations. Okay, so we've made this. What I want to do now is give an example. Actually, give it a. Should I do that? Is that safe? I'm considering changing the order. No, we'll go inside this. So now what I want to do is, so another thing that we saw at the very, very end of the last lecture is once I have the Skein category, I can make a Skein algebra, right? So from this, I also got the Skein algebra. And I can do the same thing. And this is just going to be by definitions in the morphisms of the empty labeling. So it's going to look, in this example that I drew, something like this. I have this, that, and it's going to, there's nothing's allowed to touch the bottom or the top, so it's just going to be the spanned by something like this. So it's going to be the algebra of just curves of my surface and morphisms of the empty object. So it'll look like that. And then the product is going to look like stacking. So something else. Maybe just a little curve here. So this is what it looks like. Now what I want to do is I want to give you a generalization of this where I can actually have skeins end. Sometimes I want to have skeins that end. So this is we want these two in our algebra. So let me launch into explaining how, if I don't want to just talk about closed curves in my surface as part of my algebra, if I want to have things with endpoints, how do I implement that? Is gates. And I'll just say a bit of motivation behind this. So these are adding gates. Gives us better behaved algebras. And one way that means is, we won't talk about it, but you can build a 3D TQFT out of the gated stuff, but if you don't have gates, sort of it doesn't work as well. And then the other one is, our main example will be using these things to quantize some moduli spaces, and so you can, when you add gates, you can smooth quantizations. Of smooth spaces. So that's not true for the normal scan algebra. Okay. And so that's our motivation and the idea behind how to do this is, well, if I want my skeins to end, and here I'm always allowed to color stuff, right? I could put some color here. That color is in my ribbon category. Somehow I want to build my new algebra in the sort of the ribbon categories. Themselves. And how do I do that? Well, what I'll do is I'll use, again, functoriality. So let's say, for example, I'll introduce a little notation right now. So this will be my notation for just my one disk with A in it. I'll take n of them. I do disjoint union of m copies of C. So this is just C. Disjoint union with sigma, some stratified surface, and I want to have an embedding into sigma. So let's say I give you this as part of the data. I'll call this, or fancy G, this data. And this functoriality that I've been using a lot, and we care about a lot, this will give us a functor. So what I'll do to make this functor, I'll just skip a step, is I'll just restrict to the empty stuff. I want the functor there that I'll get, so I'll call it still G. So it's going to go from this thing's Skein category times this thing's Skein category to this thing's Skein category. Something we saw before is that the Skein category of this is just A again, and this one will be just C again. So I'll get something that goes from n copies of A, n copies of M, into the Skein category. Defects Skein category of this. Now what I want to do is I want to use this structure to build myself an algebra. And there's a standard way that I can use to build an algebra from such a thing. Other questions? I know some people in the audience already think about skeins. If you're wondering, I'm building towards state skeins. I'm building towards something that's equivalent when they're both defined. But is defined more often, more generally. Okay. These things are going to be called internal Skein algebras. I'm sorry, everyone. I called this P in my notes, and if I change it to G now, I will mess up without end. Okay. So what I want to do is just say, let's just consider if I just have one disk being embedded into my surface like this. And I will call the associated functor what I want to do is I want to consider the monad of this function. Monad of the adjunction. So what's an adjunction? An adjunction is when I have one functor going between two categories. So for here it's P. And then I can associate with it sort of a left or right adjoint. Here I will be looking at the right adjoint. And if you don't think about adjunctions, the one everyone likes to think about is one of these is free, the free functor, and the other is the forgetful functor. So this is not an inverse, but it is a canonically related functor. One technical detail that I'll say just not to lie, but we won't worry about too much, is that, and actually, in this case, in order for this right adjoint to be defined, I need to work with the free co-completion. Which is also a standard construction that we don't need to know the gritty details of. And then what do I get from that? I get P, R, P. This is going to be a functor from A to A hat, like this. And what's going to do, we also have some other structures on it. So we have this. This is all just part of being a monad. P hat R. So we have that. We have natural transformation from them to the identity, and from the identity to P R. So these are both natural transformations. And what these natural transformations together let us do is treat this a bit like an algebra. So this one, here I'll write it in blue. So what this one lets me do is, if I take PR, P, PR, P, like this, I compose it a bunch of times. This part here, I can apply my natural transformation, and I can go to PRP like that. Right? So you see, in a way, I have a natural transformation that takes me from 2 copies of my functor to 1 copy of my functor. This one will act like a unit. And together these give me an algebra anytime I shoot. So what I'll do is I'll use this construction to make the Skein algebra. What's it going to be? Well, I'll call it Skein algebra of here. I'll write G. So G is this sort of functor here. I mean, I could have done this with more than just one ribbon copy of the ribbon category. So it's of sigma, and this is going to be P R identified or composed on here. So this is my construction. Let me move it to the top. And yeah, I'll admit this is a very abstract way of defining an algebra that we started off saying was just a bunch of graphs somewhere. So here's maybe an exercise that I'd be happy to go through it with you, is that if I take my internal Skein algebra for G, this thing is isomorphic to a Cohen. Has this expression like this. Where this is what we saw before. This this relative module. Okay. What does that mean for us? So what that means is that if I want to look at what does an actual element in this algebra look like? Well, with or without defects, it doesn't change much in this regard. What an element is going to look like is, so G, my functor, I had an embedded disk. Because I demanded that it came from something that also I can embed G, even though I forget this, what this means is that so this fact means that my disks were embedded at the boundary. So you can think through that sum. If I take a surface and embed it into itself, that's fine. But if I want a surface and a disk to embed into the surface, it has to happen at the boundary for sort of topological reasons. So that means that this functor P, what it's doing is it's having to insert something right next to the boundary, like that. So this is down here. This is maybe what P of V will look like. This will be colored by V. And so this is what's happening there. And then the fact that I have this relative Skein module means that then above I can have whatever Skeins going on. But they have to embed near this, at where I put this disk originally. That's one point. And then the second point is that if I want to multiply two things, so if I had this one and then, let's say, everything very wiggly like that, just to make them visually distinct, what the multiplication is going to do is it's going to first do one of them and then later do the other. So maybe I have I forget the order. So maybe my very squiggly one was here, and then my smooth one was there, like that. So it's going to push them in from the boundary, one to the other. And I will say to figure this out, you just use unity and coding data a bunch of times, repeatedly. Okay, let me introduce notation, and then we can have questions and coffee before I do the second half. So because I have to be by the boundary, I'm going to introduce some notation. So if I look at my surface sigma, and my disk was embedded here, so this little region is where all my endpoints can be. The fact that it's on the boundary, I'll draw it like this. I'll just draw the same boundary sigma, and I'll take the two endpoints of this and I'll put it like this. So if I had a skein here coming out, I'll just say it's on this. So that's just an easy way to do it, and I'll call this thing the gate, because it's where things can enter my Skein algebra. Okay, I think, yeah, this is actually a very natural stopping point, so let's pause here.